I mentioned before we took the break that in this design here we have a constraint that for one supplier number there's one city. Whenever we see supplier 1 in a tuple here, we have to see London as well. In fact, there's a business rule we're talking about here. The business rule is for a given supplier there's just one city. And if there's a business rule, that means there's an integrity constraint that needs to be stated and enforced. But this particular constraint is an example of a very important special case called a functional dependency, or FD for short. A very important notion, the functional dependency. I've heard functional dependencies described as not quite fundamental, but very nearly so. Here's the definition. Let x and y be subsets of the heading of rel var R. So x and y are both sets of attributes of rel var R. Then the functional dependency x arrow y holds in rel var R if and only if, whenever two tuples of R have the same value for x, they also have the same value for y. So in this rel var here, there's a functional dependency from supplier number to city, because whenever two tuples have the same supplier number, they have the same city. So we write it x arrow y. X and y, I say again, are both subsets of the heading. X, the left-hand side, the formal name is the determinant, and the right-hand side, the formal name for that is the dependent. But frankly, I think the easiest way to read this stuff is just to say x arrow y. That's what I will say. So in our example, we have supplier number arrow city holds in SPCT. Note the braces, because the left-hand side and the right-hand side are both sets of attributes, even if the set contains just one attribute, as it does in this example here. As a matter of fact, of course, not only do we have an arrow from supplier number to city, we have one from supplier number to status. For one supplier, there's one status, right? That's a functional dependency as well. So we can combine them. We can write them as a one-liner, supplier number arrow, city comma status. Whenever two tuples have the same supplier number, they have the same city status combination. That's true. Note the braces. It's just like the stuff with keys earlier. X and y here are sets of attributes. X values and y values are tuples. Subtuples probably of some other tuple, but still tuples, because remember, a subtuple is a tuple. Just as keys are sets of attributes and key values are tuples. Which brings me to my next point. If K is a key for rel var R, here the key, I didn't say this before, but in fact it's the combination of supplier number and part number. If K is a key for R, then the functional dependency K arrow A necessarily holds for all possible attributes A of the rel var. Because think about it. K arrow A says whenever two tuples have the same value for K, they have the same value for A. Well, if two tuples have the same value for K, and K is a key, they are the same tuple. And therefore they must have the same value for everything else. So there's always a functional dependency arrow coming out of a key to everything else. Those FDs are always there. You can never get rid of them. An equivalent way of saying the same thing is if K is a key for R, then K arrow X holds for all subsets X of the heading of R. These two both say the same thing. So that there's always these arrows out of keys. You can never get rid of those. Loosely speaking, it's if there are any other arrows that we have a problem. The problem with this thing here is going to be that there are arrows that are not arrows out of keys. That's what causes the trouble. One more piece of terminology I have to get out of the way before we can start focusing on these normal forms. If x arrow y holds, this is a useful thing to remember, by the way. If x arrow y holds, then you can always add attributes to the left. You can always take attributes away from the right and the result will still be an FD that holds. So if x arrow y holds, x prime arrow y prime holds as well for all proper supersets x prime of x and all proper subsets y prime of y. Let me illustrate. In this thing here, we have S number, arrow, city, comma, status. Therefore, S number, P number, arrow, city holds as well. I can add an attribute to the left-hand side, it makes no difference. I can take attributes away from the right-hand side, it makes no difference. So this is a way, if you like, of generating new FDs from given FDs. And now, if x prime arrow y holds, and x arrow y does not hold for any proper subset x of x prime, then x prime arrow y is irreducible. We can't drop any attributes from the left without having something that no longer holds. So that the left-hand side is as small as possible. It's irreducible in irreducible FD. So again, looking at our example SBCT, S number, part number, arrow, quantity is irreducible. If you drop an attribute from the left-hand side, what you get is no longer true. It's not true that supply number, arrow, quantity holds. It's not true that part number, arrow, quantity holds. Quantity is dependent on the combination of supply number and part number. You can't drop anything from the left, so that's irreducible. By contrast, S number, P number, arrow, city, this one here, that certainly holds, but it's reducible. We could drop the part number, and supply number by itself, arrow, city, that holds. City depends only on the supply number. You don't need the part number. This stuff is really easy once you get your head through the terminology. So given that notion of irreducible FDs, I can now define the second normal form. R is in second normal form if and only if, for every key k of R and every non-key attribute A of R, a non-key attribute is an attribute that's not part of any key, k arrow A is irreducible. Now, we know that k arrow A holds. There's always arrows out of keys. That FD definitely holds, but it might or might not be irreducible. You see, the problem with SPCT here is that it's not in 2 and F, because the key, the only key, is the combination of supply number and part number. So S number, part number, arrow, city certainly holds, and S number, part number, arrow, status certainly holds, but they're both reducible. We can drop the part number. So what we have here is arrows out of, not out of the whole key, but out of a piece of the key. That's what's wrong with this design. We have something over here that is functionally dependent not on the key, but on a proper subset of the key. That's why it's not in second normal form. Second normal form says these arrows out of keys must be irreducible. I'm sorry, Lauren?
So you're saying that second normal form is better than first and third is better than second, etc. Yeah. It seems to me like the more or the higher normal form you get, the more kind of convoluted your table structure becomes. Is that just because this sample is so simple? Does that become more apparent with like larger?
The comment is that the higher you get in the normalization process, the more convoluted the table structures become.
You end up with like 6 or 7 tables when you can.
Well, you certainly wind up with more tables, yeah. More roll bars, I prefer to say.
Sorry.
Yes, but the individual roll bars are more simple. See, this I regard as convoluted.
Okay. Because
it's, what you're really doing in this roll bar here is you're representing too much different information. You're representing the fact that a certain supplier has a certain city, which is a property of a supplier, but you're also representing the fact that a certain shipment has a certain quantity, which is a property of a shipment. Okay. So you're muddying two very different predicates in one roll bar. Okay. And what the normalization process is about is breaking roll bar predicates apart so that they're sort of more independent. I regard that as the opposite of convoluted, but I see what you mean. You do wind up with more roll bars, usually. So back to my example, these two FDs hold. They are arrows out of the key, that's all right, but they are reducible. and they are what cause the redundancies and the update anomalies. And so the normalization discipline will say, okay, break the rel-var down to get rid of these reducible FDs. And there's a theorem that helps us in this regard. So if rel-var R is not in 2NF, the principles of further normalization say decompose it into projections that are in 2NF. That's exactly what I did in my example before. It turns out the two projections were both in 2NF. As a matter of fact, they're both in Boyce-Codd normal form. The theorem that helps is called Heath's theorem. Ian Heath came up with this back in 1971. Let x, y, and z be subsets of the heading H of rel-var R, such that the union, the set theory union of x, y, and z is equal to H. So all of the attributes are in x or y or z or some combination. For simplicity, notation, let x, y denote the union of x and y, and likewise x, z is the union of x and z. Here's the theorem. If the functional dependency x, r, or y holds in R, then R is equal to the join of its projections on x, y, and x, z. And that means it can be broken down in a non-loss way into those two projections on x, y, and x, z. You see, we have supplier number arrow city here, and supplier number arrow status. So we have supplier number arrow city and status. Heath's theorem says we can break it down then into the projection supplier number city and status, and the rest, supplier number, part number, quantity. That's exactly what we did. We applied Heath's theorem to the decomposition of this bad design, and we wound up with two rel-vars that actually happen to be in 2NF. Now, let me just elaborate briefly on this. Let's assume for simplicity that x and y and z here are single attributes. Now, Heath's theorem does not say that. They just had to be subsets of the heading. But suppose we're talking about degree 3. There are just three attributes, x, y, and z. So we have R, x, y, z satisfying the functional dependency x, arrow, y. Heath's theorem says we can break it down into R1 containing attributes x and y, and by the way, x will be a key here because of this functional dependency, and R2 on x and z, and x here will be a foreign key referring to the key x up there. So that's basically what I did in the example. But I say again, the theorem doesn't require x, y, and z to be individual attributes. It just requires them to be subsets of the heading such that their union is equal to the whole heading. It doesn't even require them to be disjoint. They can overlap, they can have attributes in common. It still works. So that's a good place again to take a break and let you meditate for a while on that one. When we come back, I'll do my third and last session on this business of normalization and database design theory.